the textbook and back up to beginning. So nobody has any questions, or you must have written down some things as you were reading, or found some things that might have been a little confusing that you might want to ask about.
I had one like basic question. Maybe.
Sure.
So in the decision function right here, they mention like, you know, it's the W transpose X plus B. And then when he's talking about its slope, they mention that it's like the norm of W. But wouldn't it be, if you're taking the derivative with respect to X, wouldn't it just be W transpose?
Yeah, I was a little confused by that too. Yeah, so in this, so if we look at this three-dimensional hyperplane, three-dimensional space here, where this is the a part of the iris classification problem, where we're just looking at the 2 dimensions, petal length and petal width. So he plots all the points, and then on the vertical axis he plots the decision function, W transpose X plus B. So we're seeing that, and and then the decision line is the place where the decision function intersects this plane. So the petal length versus petal width plot is a 2-dimensional plot, right? It's all contained in this blue square. The decision function is a 3rd dimension. It's the sort of the z dimension, and so the decision function is the line of intersection of these 2 planes. And then he says that the slope is the norm of W transpose, and I'm not exactly sure why that is true. So yeah, I share your confusion on that, and it's a good question. Does anybody else have some insight into this? So let's see. He says, where does he actually say? Yeah, the slope of the decision function. But then he's talking, it looks like he might be talking about this 1-dimensional version of the problem where you're looking at the slope of the decision function against only one of the variables. So here's x1, and here's the decision function, the component of the decision function, w1, x1. And so maybe it's this slope that he's talking about.
I think he used the 2D one to show the point that if you decrease the slope, the margin increases, so the street gets wider. I think
yeah.
That.
Yeah, and that's shown in these two, in this plot here, right? The smaller slope means that the distance between the 2 points that reach the margin of plus or minus 1 are closer together than they are with the shallower slope, right? So these are the 2 here. These 2 points are the ones that reach the margin of minus 1 and plus 1. So it's this point maps to minus 1 margin, and this point maps to plus 1. So they're farther apart. So this is maybe just the justification for minimizing, in some way minimizing the norm of W, because the smaller W is, the wider the street would be, is the idea. The question that I had was, when I read this was, or one question I had when I read this was, why can you say that the margin is plus or minus 1 for the hard margin? So, if you look at the graph on the previous page, he draws the margin. The dotted lines are at a distance of of 1 in either direction from the decision boundary. So I guess the question that I had was, why can you do that? Why is it plus or minus 1? Why isn't it plus or minus a half or plus or minus 0.1 or something like that?
Joseph, that is just an example. So as you said, it can be any value for the just exploring the thing. And if you go to the code as well, he has hard-codedly done that thing. For the decision boundary, he has taken the equation represent wx like w dot x plus b is equal to 0. That is the hard line, that is the solid line. And if you go through the dotted line, that he has come up with the explicit value of plus 1 or minus 1. So that is just an example that it can be. So decision boundary for this time, he is taking a decision boundary of being, a margin of being plus minus 1. But along with that value of w, if we change the value of w, then the other values can be there as well.
Yeah, so here's the equation for what he calls the hard margin problem, where you don't allow any violations.
Right.
And he casts it in terms of this special. He maps the y's into a y equals 1 gets mapped into a t of 1, and a y equals 0 gets mapped into a t of minus 1, and then you can represent the condition that the points must be within the margin by this one single equation. But again, the margin is supposed to be plus and minus 1. So this is supposed to be generally true for the hard margin condition.
This is because of the thing that if you think it mathematically as well as functionally, if you want to put a point classification wise, if you want to put a point as positive class or negative class, in that case, the value has to be greater than 1. So if you say that the value of the class is 1, so in that case, it has to be greater than 1 to be off the road. So if you consider it, if you come down to the previous page, just beneath the diagram, there he explains that thing. That for being some point being in the positive class, it's that value w transpose x plus b, it has to be greater than 1, because 1 is considered as a class. So if your value is greater than that one, in that case only you can say that this is positive class, and for the negative class, other way around.
But if you look at the this equation, really the only the only requirement is that this thing be greater than 0, and that puts it in the positive class. And if w transpose x plus b is less than 0, that puts it in the negative class. But now we're introducing this extra requirement that that it not only has to be it has to be within the margin as well. I mean, it has to be outside the margin. In other words, the decision, back to this graph, the original problem is cast in terms of this decision boundary. That is, if wt plus b is, see here it is right here. The class is classified 0 if the dot product, if wtx plus b is less than 0, 1 if wtx plus b is greater than 0. That's this solid black line. But now we're requiring something more stringent. That is, we're saying it's got to be not only above this line, but it has to be above the dotted line as well. And a negative class has to be not only below this line, but below the dotted line as well. So it seems like we're introducing sort of a harder condition to satisfy. And it seems arbitrary that we should have chosen a margin width of 1. That's the thing that's a little confusing to me.
Joseph, that's what makes it maximum margin. If we stick with hard margin, then that's what, otherwise it's similar to logistic regression classifier. And what makes it a hard margin for right now until we relax it is the extra, the street that we introduce that by now. To your question about the choice of 1, it's just a convenience. And that's the way the MIT as well as the Andrew Ng explain it, as a convenience choice of 1, which makes the math simpler as we move forward. But why the choice of greater than 0 is to ensure that there is a street there instead of a single line. Right.
So, and I presume that the choice of 1 can be justified by rescaling the data in some way, so that it can always be done to make a street of width 1. But anyway, so yeah, so that's that. Okay, so that's the hard margin problem, and now he talks about, well, some problems will not have a solution. There won't be a street that cleanly separates all the positive and negative classes. And so in that case, you can still do this problem. You can still do it this way, the way of trying to define a street between the positive and negative classes, if you now allow margin violations. So let's be clear of our definitions first before we talk about this. The margin is basically this, are these two dotted lines, right? And they're defined at a distance of 1 away from the decision boundary. So that's what we mean by the margin. And then when he talks about a margin violation, he talks about introducing a slack variable where zeta, that's what this letter is, Greek letter zeta, for each data instance, and zeta measures how much that instance is allowed to violate the margin. So I'm not sure what he means about allowed to, because he's actually saying whatever it is. I mean, in other words, zeta is the distance away from the margin for that example, or well, I don't know. Zeta is, I guess, the zetas are parameters that now a whole new set of parameters that have to be solved, and they can be different for each example. So you have, like, if there's m examples in your data set, then you have m values of zeta that you have to solve for. Let's see. So he calls these zetas slack variables, and they have to be positive. So now the condition becomes relaxed, and instead of having to be greater than 1, it has to be greater than 1 minus zeta. And I think, I think zeta has to be, yeah.
If I can explain for a minute the thing you said about making the slack. See, the reason he phrases it that way is because depending on where you choose the classifier line, your zeta will also vary, as will your width. So it's not that zeta is constant. The zeta can be of each point will be different depending on where you draw that line. So the line that classifies as 0 or 1. Hence, zeta is not fixed for each instance. It also depends on where the line is drawn. Once the line is drawn, you're right. The zeta is fixed for each value of x. But depending on the line, the zeta will shift, right?
Yeah, but the point, I guess, is that for each instance, for each data point, you have a unique value of zeta that you have to solve for in this problem.
That's correct. And also, just to clarify, the optimization problem that you are solving is still the first one. The second one is a constraint that you now have.
Right. So SVM, support vector machines, is all about constrained optimization problems. Even the first one, even the even the hard margin problem was a minimization problem, which we're used to seeing from gradient descent. But what we haven't seen is that we have to impose on top of it a constraint. In this case, a linear constraint, linear in the parameters W. So it's basically a quadratic minimization problem with a linear constraint. The soft margin problem is also a quadratic minimization because we're minimizing a quadratic function, but now we also have, and now it still has linear constraints. So the point of this, I guess, the reason what makes support vector machines so great is that quadratic functions are convex. As we know, quadratic functions have a single global minimum, right? If you think about a parabola. So this is a solvable. It's a convex problem that means that you can actually find the global minimum. And there are methods called quadratic, there are mathematical methods called quadratic programming that allow you to do that. And there's third-party products that you can go off and solve these quadratic problems. Of course, scikit-learn has these things built in, when you use the SVM classes. So,
Joseph, I have a question here.
Yes.
Yeah. Now, regarding this convex and quadratic, both these things. Now, regarding a parabola or something like that of the lower order, we can understand it's a convex problem, like convex function by looking at the graph of it. Now, if there is any nth order problem, and how can we decide whether it's a convex problem having a global minima just looking at the function of it without actually plotting the graph? Is there any way?
Well, I guess the point here is that this is all there is. It is quadratic, and so we already know that it's convex. I'm not sure I understand the full question.
No. My question is that here it's a quadratic, so by that means we can understand it's a convex problem.
Yes.
Now let's say there's a nth order problem, x to the power n or something like. I'm not talking on this context. Generally, I'm talking. So if there is any nth order equation, by looking at the equation, can we come to any conclusion just by looking at the equation, not by plotting its graph? Just by the equation, can we decide whether it's a convex equation or not?
Well, if you look at a cubic, you know that a cubic isn't convex, right? Because it has it has inflection points where it changes direction, and so a cubic is generally not convex. So yeah, so I mean, I'm not sure I know how to answer the question, but I think the point here is that for support vector machines, it is quadratic, and quadratics we know are convex.
Right. Okay.
Yeah, but I don't know how to answer the general question that you asked. That is, looking at the equation for something, can we determine whether or not it's convex? Sometimes you can determine whether you can say that it's not convex. Like if you see a cubic term, you know that that's not convex.
Right.
Let's see. Okay, so here's the general form of a quadratic programming problem. You have a quadratic function. You're trying to minimize some quadratic function, and this is more general than our problem. In our problem, it was the W transpose W, but in a more general problem, there can be a matrix in between. And H isn't part of the problem. It's P that you have to solve for in this problem. So you have a quadratic term and a linear term. And then you have a set of linear constraints that's given by this matrix A, the two-dimensional matrix A and the one-dimensional column vector B gives you a set of constraints. So this is sort of the general form of a quadratic programming problem. And he shows that by considering different values of these things, you can map this, and you can see how this maps into either the hard constraint, the hard margin problem, or the soft. And in the exercises, I guess he says they show how it maps into a soft margin problem as well. Okay, so that's so that tells you sort of what's going on with SVM. We have to depend on these quadratic solvers, which are built into the scikit-learn SVM classes to solve the problem. So now he segues into this thing called the dual problem. And again, this is something you have to accept on faith, unless you want to go to Appendix C and show how it's derived. But given a problem in its normal form, which he calls the primal form, that is here we go. Okay, so this would be the primal form for hard margin problem, the quote-unquote primal form for the hard margin problem, and the primal form for the soft margin problem. He says that it can be shown that you can map this into a dual problem where you're solving for, instead of W's, you're solving for these alphas. And the interesting thing about the dual problem is that it involves the dot product, the inner product of the data vectors. And that means that we can, and the other interesting thing, of course, is that if you solve this problem, so this is again a quadratic problem. subject to linear constraints. So again, you can use a quadratic solver to solve this problem. And then he shows that there's a way to map it back to the primal problem. So why go through all this trouble? It turns out then if you map the problem to the dual problem, and then you go to all the trouble to solve it, solve for the alphas, then you can use the alphas to solve the primal problem, which means finding the W, the weights vector, and the bias. So why do we want to do this? Well, there's two reasons why you might want to do this. And one is, it turns out that if you have more features than data, than samples in your training set, in other words, if you have like 1,000 samples and each sample has 10,000 features, that kind of a problem, it turns out that the dual problem is faster. Solving it with the dual is faster. So that would be one reason why you'd want to use the dual. Does that make sense? Most problems, you have way more data points than you have features, but that's not always the case. Sometimes you have to solve for a lot of features with only with less number of data points. And that kind of problem, it turns out that the dual problem can be solved faster. But the main reason to use the dual is because this is how to implement what they call the kernel trick. Okay, and the kernel trick is the idea of mapping your data vectors to a higher dimensional space where you can more easily find a separation, find a decision boundary that separates the classes. And the reason why the dual problem is amenable to the kernel trick is because it involves the dot product, the inner product of the data vectors. And and how does that work? Well, so the next thing he shows you, let's suppose we define some kind of a mapping, a quadratic mapping. In other words, each of the we start out with two-dimensional data, and we map it into a quadratic function, and now we have 3 dimensions of data. We have one for the x squared term, one dimension for the x2 squared term, and 1 dimension for the combination of the x1 and x2 terms. So from each of our data points, x1 and x2, we can map them to a 3-dimensional data point. This is a polynomial. This is what's called a quadratic kernel, right? So the phi is basically the mapping of the data point into a higher dimensional space. So so now in that higher dimensional space, the dot product, that higher dimensional space should also have a dot product. And if we express the dot product, it would look like this. Phi of A transpose, that would be this vector, because this tells you this is the recipe for how to map A. That gives you this to the higher dimensional space. And this is a recipe for how to map B to the higher dimensional space. And so you take the dot product of the mapping, and you end up with this. And it turns out that that this function is a function only of A1 and B1, and it can be represented as a function of the dot product of A and B. So this is the dot product of A and B, and it turns out that this thing is the same as this thing if you just factor it, and then A1 B1 plus A2 B2 is just A1 is just the A vector dot is just A dot B, right? And the whole thing is squared, so it's basically just A dot B squared. So the interesting thing that he points out is that and this is also called the kernel, the quadratic kernel. So it would be K of A and B in his notation later on. So the idea is that if you have the kernel, if you start out with a kernel function, which is a function of the dot product of A and B, you don't really even have to know the mapping. You just knowing the dot product is knowing the kernel function is enough. So now he talks about different kinds of kernels. The linear kernel is just A dot B. The polynomial kernel would be a general polynomial. So you'd have A dot B plus some constant and then some scale factor, and then raise that to the D power. And what we just saw previously was a polynomial kernel with degree equals 2, right? Here, d would be 2. D is the degree of the polynomial.
Joseph, before
Yes,
we
sir.
go too far away, can we go back to the previous page?
Sure.
One thing is bothering me. Equation 5.8 on this next page, on the second page on the right of the top. So for that, wouldn't that be the equal to plus minus root 2 x1, x2? Plus, and it's that plus minus, and because we're dropping the minus.
Well, no, I mean, if you take x1 plus x2 squared, these are the, yeah, I'm not sure why that square root of 2 is there.
Exactly.
I'm not sure why that's square. The point is, you want the quadratic function of x1 and x2 means you have to have a squared term for x1, a squared term for x2, and a mixing of x1 and x2.
X1 and x2.
Yeah,
and x1, x2 two times. It's x1 square plus x1, x2. Where again, it depends on how you define it, and that's why I was going to say in this case it uses a simple example. You can take 3 x1, x2, x3, and then it becomes more obvious. But sticking with this, it's just all combinations of x1 and x2. So it's x1 square, then it's x1, x2, the product. Then again, x2, x1, and x1, x2, and x2, x1 are the same. And then x2 square. So 2 entries, or from 2-dimensional space, you go to 4 dimensions. x1 square, x1, x2, x2, x1, and x2 square. And he just simplifies it, unfortunately, in my opinion, by combining the x1, x2, and x2, x1, saying it's the same thing. So it becomes 2x1, x2. And then when you take, he just square roots that. But instead, you can just leave it as x1 square, x1, x2, x2, x1, x2 square. So if you had x1, x2, and x3, then you would have x1 square, x2 square, x3 square, and then all combination of 2 elements.
All the cross terms. Yeah, all the cross terms.
All the cross terms. And so that will become 9 terms. So in fact, one of the interesting things it's pointed out in other lectures is when you take the dot product, the computational efficiency of the A transpose B whole square is it's linear in the terms in A or in B. Whereas if you did the transformation, it is of the order of n square, as you can see, meaning if you have x1 and x2, it's 4 terms. If you have x1, x2, x3, you have 3 terms, which then expands to 9 terms when you transform. So in effect, when you do these parameter transforms for just the kind of transform we are talking about, then in the transform space, you would actually be if you were to perform the transform, you would actually be operating on n square terms. Instead, when you just stay in the current space, you're operating in linear space, which is the original space of just 2 or 3 dimensions in this example.
Right. So in general, you just need, for a quadratic function, you just need to have combinations of x1 squared, x2 squared, and x1, x2. I don't think you really need another one for x2, x1 because it's commutative. But and then they threw in this square root of 2 because that makes things work with when you take the dot product. Because without this square root of 2 here, you wouldn't get the clean, you wouldn't get the function of the dot product to come out. So square root of 2 was chosen deliberately to make that work.
Yep, and so the operative word there that Srinivas said, defined. This is how he defines it. That made all the sense for me.
Yeah. So it's defined. It's defined in this way because that makes it expressible. That makes a dot product of phi's expressible in terms of the dot product of the original vectors.
So in that case, the root 2. Is it kind of a back engineering? First, the intention is to create the situation that phi A transpose phi B is equal to A transpose B whole square. The intention is to come up with something like that, and whatever function fits the bill, he goes with that function.
That's correct. So in a longer sense, we'll see that certain restrictions apply to kernels, and they have to behave in a particular way. So yes, you're right.
So
What
yeah,
is the maximum constraint?
so the polynomial kernel is this, and then we talked about the Gaussian radial basis function. But the kernel trick, the kernel function is basically a function that can represent a dot product in a higher dimensional space. And in order to be able to do that, it has to satisfy this thing called Mercer's conditions. And Mercer's conditions are basically that the function has to be continuous, it has to be commutative, and that is the kernel. It has to be continuous, it has to be commutative, that is k of AB has to be equal to k of A of BA. When you reverse the A and B, it has to be equal. So it has to be symmetric in A and B. And then the third condition is that that the kernel matrix, the matrix representing the kernel has to be a positive definite matrix. And that is something that that you can look up, but basically any kernel that satisfies those three conditions is the dot product, or is the dot product for some higher dimensional space, for some higher dimensional transform phi. And we don't really even have to know what that higher dimensional transform is to be able to use this mapping. So so that's basically the kernel trick, is that you can is that when you have a dual problem, all you have to do is substitute the xi and xj into the kernel. In other words, you can substitute the kernel function for xi and xj, and if it's a quadratic function, then that meant you used xi.xj squared instead of xi and xj, and then you go ahead and solve that problem. If it's a radial basis function, it looks more complicated.
Just one question here. Now, regarding this function kernel, if you can just go to the previous page. Here here the equation is regarding the phi A transpose phi B is equal to A transpose B whole square. So the point he mentions below is that calculating phi and then transposing it, and then calculating phi B, then multiplication, that's a compute intensive task. With regards to A transpose B is a much easier task. That's the whole point of going with the kernel.
That's what Srinivas said, right? I mean, in other words, calculating a dot product of an m-dimensional vector requires m multiplications, whereas to do the mapping and calculate the product, it's on the order of m squared, right?
Right. Now, if you could just go to the next page.
Yeah.
Now here he is talking about minimizing this equation. Let's say any equation is there, any cost function that we are trying to minimize. In that function, first some phi has to be there, which we can replace with the normal A transpose B whole square. But where from the phi comes, if you go to the any cost function that is written here, probably it's in the previous page probably. If you could just go to the previous page.
Okay, so are you asking a question about this equation here?
Exactly, I'm just finding that one. Can you go to the previous page?
Yes.
There is one function which is we are trying to minimize. Right. If you see the big white box on the left hand side, W
yes.
transpose and B transpose, this is actually what we are trying to find here. So in this equation, there is nowhere phi to be found. So how exactly he is applying that thing, that phi A transpose phi B is equal to A transpose B?
So in the higher dimensional space, the problem will be represented not in terms of x, but in terms of phi of x. So that's how the phi of x comes into the problem. When you map the problem to the higher dimensional space, that's where the phi of x comes in. You're basically changing variables from x to a new variable called z, maybe, and z equals phi of x.
So in that case, are we going to calculate for phi of w hat and phi of b? Is that the understanding?
We're actually not going to have to calculate it, because all we need is the dot product given by the kernel function. So that's the only thing we need to calculate. And these kernel functions, as you see, are simply expressed. So the idea of a kernel function is that it's these kernel functions, the main ones that are being used are polynomial Gaussian. And they point out that the sigmoid function doesn't satisfy Mercer's conditions, but people use it anyway and sometimes gets good results. But it's not It's not based on principle. It's based on just convenience.
Joseph, a request. If you could just go back to the previous page for a second, I'll try and answer. So here's my attempt at answering your question. Phi is the transformation that you would want all of the vectors to go through in order to transform your entire problem into the higher dimensional space. So phi is the transformation that you apply that you wish to apply in order to take all of your points from your current space to the higher dimensional space. But what this mathematics shows you is you do not need to go through the trouble of translating all of your points to the higher dimensional space and applying that phi transform. Instead, if you just calculate the dot product of the two vectors or the support vectors, that is, you calculate the dot product of the support vectors in the current space using the kernel, that is equivalent to translating all of your input points into the high dimensional space and doing the math there. You don't need to go through the trouble of applying phi. Instead, you only use the kernel, quote, kernel trick, to calculate the dot product of A and B in your original space using the kernel. That is equivalent to transforming your data to the higher dimensional space. That's the beauty of SVM, that you are transforming the data by only calculating the dot product in your current space.
So by this trick, once I'm done applying the kernel and everything, the output will be in the higher dimensional space or in the original space only?
That he'll do the math and show you that when you, in the higher dimensional space, it will be linear. When you bring it back to the current dimensional space, that's when you get the arbitrary shape that you want.
Okay. So thanks, Srinivas.
So when you map the problem, if you transform the x's into, by using the transformation phi, then you get a new problem. But the problem involves the dot product of the phi's. It doesn't require you to know the phi transformation. It just requires you to know the dot product of the phi's. And that's given by the kernel. And so basically you can, wherever you see the x, like you go back to the, wherever you see the x dot product, you just replace it with the phi dot product, that is the kernel function. And that's the equivalent problem. So that's the kernel trick. It's basically replacing the problem in your lower dimensional space with the phi of x dot phi of j, which is the kernel that maps it to the higher dimensional space.
And if I might for a minute, if you indulge yourself and watch the Patrick Winston's lecture in MIT, I mean, he says something which makes you, especially if you're interested in math, just marvel at it, right? It doesn't have to have simplified to a dot product. The fact that it did is what enables SVM to work its magic. And that is the beauty as well as the marvel of mathematics. I mean, it didn't have to be this way that it simplifies to the dot product of the support vectors, but it does when you work the math, which is what leads to the beauty of the math simplification of calculating the dot product in the current space, yielding you the separation in even the infinite space. That's when you have to admire or marvel at the beauty of math.
Yeah, he does mention that you could actually, that your mapping can be to an even to an infinite dimensional space. And contrary to what we've learned before is that, when you use higher dimensions, when you make your models in higher dimensions, you suffer a penalty for for overfitting. But it's not the case here, because we're not actually mapping the function. We're not actually mapping the function to higher dimensional space. We're just using the kernel, and so we don't suffer the penalty of having more variables. In other words, a model that has more variables and therefore is subject to overfitting.
One more question on that. Does that mean that this kernel trick is computationally more efficient, like big O notation, easier to compute than doing it fully?
Absolutely.
Yeah. Yes.
That's what I went through, right? Order of n versus order of n square when you have to do the transformation. So yes.
Yeah. Thank you.
Yeah, because dot products are ON. So let's see. Question.
Yeah, I had a quick question.
Yeah.
So I've read before, like some time back, that like finding the kernel is almost like an art. Any thoughts about that? Like, like finding the right kernel for your problem.
I haven't. I'm sure that people work with fancy kernels that are more applicable to their problems, and yeah, once you come up with something and you show that it satisfies Mercer's conditions, then you can go ahead and use it as a kernel. So I don't know anything about that art, but I do know that almost anything. This is kind of like the Swiss Army knife of kernels, and most problems can be attacked with the Gaussian radial basis function kernel, and it works very well.
Okay, and second a more note, like, I know there's a result like with just a comparison, right, of classifier. So there's a result with the base classifier, right, that if your features of the class, if they actually had a Gaussian distribution, or if you knew the distribution, right, nothing can beat the base classifier, right? There's a base error rate and there's all that mathematical proof. But the biggest problem, like in real life, is you don't know those distributions, right? So, but is there like some domain or some problems like where SVM would be like more suited? So I know one of the previous talk, Srinivas or someone said that, you, or maybe Joseph, that it's good for medium-sized data sets. But
yeah, complex models with medium-sized data sets, and I think he mentions in the text that 1,000 to 10,000, maybe even less than 10,000 data points, but highly nonlinear problems. In other words, if the problem is highly nonlinear and there are 1,000 to 10,000 examples, that's kind of like the sweet spot for SVM. But
okay,
larger problems, he wouldn't recommend using it. And also, I listened to the Caltech lecture that was suggested, and in that lecture he says that supported vector regression, which he talks about at the sort of in this chapter, that is not the best way. That is not generally a very effective method. So people don't really use that very much. They mostly use it for classification.
Yeah, two responses, Mel. One is, if you listen to the Andrewing lecture, the second one especially kind of addresses your question of how to go about selecting kernels. But again, you need more detailed math knowledge and knowledge of, as you said, the distribution in order to pick which of the distributions. And therefore, in general, for most problems, what Joseph said applies. Use one of these, go with Gaussian as the default, and you're pretty much set. Now, having said that, obviously, if you're specialized and you want to do more than that, then you need to understand the distribution you have, and he gets a little bit into it, and also the generality of the kernel trick and its application to other cases where it applies. And he also, in a different note, and I have it from my notes, in different lectures, just like Joseph mentioned, Andrewing also gives a set of directions on when to use logistic versus linear versus SVC versus blah, blah, blah. And, since I have it written down, I'll post it in the Slack channel later.
Awesome. Thank you so much.
Is that the machine learning yearning book, Srinivas?
No, it's somewhere else. I think it's
one of his lectures?
One of his original machine learning classes, but I just have it written down. So let me just post it. And if, by the way, people find counter examples or where it is not correct, then feel free to comment on it. But since I have it jotted down, I might as well share it.
Srinivas, are you referring to Abu Mustafa's class at Caltech, or?
No, that was Joseph's reference. My reference is to Andrewing's class, and I don't know whether it was his original machine learning at Stanford or subsequent
Andreas
to
Muller.
Coursera.
Yeah, Andreas Muller, who's also one of the coders for scikit-learn, his class at Columbia is also on YouTube. The one from 2019 is the one that I used for this. Just
interesting.
Yeah, no, I was specifically referring to the size of problem and when to use which technique, and that's appropriate.
Yeah, thank you.
Yeah. So Mash, do you want to post those lectures on, or have you already posted them on the Slack? The ones by Andreas Muller?
I'll do that right now.
Thank you so much. Yeah. Let's see. I noticed a question from Siva. He said, does a quadratic problem refer to minimizing a quadratic function relative to only linear constraints, or can there be higher order constraints? Are there off-the-shelf solvers for that too? I know that there are off-the-shelf solvers for quadratic problems with linear constraints. I don't know about higher order constraints. So that's a good question that I can't answer at this point. Okay, let's see.
This is one question. This searching for the kernel is a hyperparameter optimization problem. Like, can we do it using grid search?
What do you want to find with grid search?
The kernel, which kernel do you want to use for a particular problem?
Yeah, I mean, in a way, you could try it with you could try the problem with a, with a polynomial kernel, and then see if you can do better with a radial basis function kernel. And again, you can use a grid search to take you through some parameters, some to the parameter space. Because here in Gaussian radial basis function has only one parameter, so that you can use a grid search to go through different values of gamma. And there are probably on the web somewhere, there are recommendations of what are the good ranges for gamma. For the polynomial, you have you have three parameters. You have the degree, the constant, and the gamma. So that would require more time to do a grid search. But yeah, you could certainly do that and then see which, if you have time and compute resources available, you can see which model gives you the best result.
So just one question in this regard. Whenever I run the code associated notebooks in the Colab, for most of the cases, specifically for cross validation as well as for grid search, it gets awfully slow. So is there any suggestion to optimize that or make it fast?
That's a good question. Yeah, I mean, that's just the problem with grid search. You can do, you can explore lots of parameters, but it takes a lot of compute to do it.
I tried using TPU as well, but it doesn't seem to help.
Even TPU doesn't go fast, huh?
Right.
Maybe make your grid smaller, or.
Okay. Actually, I'm
that's
just
the only
running
suggestion.
a notebook, and in the notebook itself, he has explicitly written that be aware that this cell is going to take a lot of time, etc.
Yeah. So how long does it take? I didn't run that to completion. How long does it take in the notebook?
Frankly, I tried for 30-40 minutes for a cross validation, and after that I stopped it.
So I guess you have to go away. You have to set it at night and then go to sleep and wake up in the morning.
Exactly. Before the cell, he actually explicitly did that. Be aware that this is going to take a couple of hours. So
okay.
I didn't take any more chances.
Okay. Okay. So where are we? So we talked about Kernel Trick. He talks about online support vector machines where you have to solve the problem. You only get to hold some of the data in your memory at a time. So that's where this gradient descent classifier comes in, because you can do it in you can do it stochastically. You can do it one sample at a time, or you can do it in small batches. So I'm not sure. So he says that it's slow, and then he says you have to use this cost function, which is called Hinge Loss. And here he gives a graph of what it looks like. So it's given by this function max of 0 and 1 minus t. So you can see that as long as t is greater than 1, that's going to make it 0, because then 1 minus t is going to be negative, so that's going to be all 0. And then when t is smaller than 1, then the hinge loss is just greater than, sorry, when when t is smaller than 1 or negative, then 1 minus t is, then it's just going to be 1 minus t, because it's always going to be greater than 0. So that's what the hinge loss looks like. It's kind of like, it kind of looks like the ReLU function a little bit, except in a mirror image.
And shifted.
Yeah, yeah, and shifted as well. Yeah. Let's see. He says you can use lasso. You can still use. So if you use lasso, you know, you're working with an absolute value function which doesn't have a derivative. The hinge loss function doesn't have a derivative at t equals 1, but then he says that it works if you use what he calls a subderivative, a subgradient, which is some value between the gradient here on this branch, which is 0, and the gradient on this branch, which is -1. So you just put some random value in there for the gradient at 1, and it works okay, I guess. Yeah. So that's online. He talks about other implementations of online kernelized SVMs. I didn't read these papers, but apparently they give good ways to do it. And then he says for large-scale problems, you probably want to use neural networks, which is, yeah, that's what he says here. Large-scale nonlinear problems. Large-scale meaning, I guess, more than 10,000 data points. Yeah. So I think we covered it. I think we covered all the rest of the chapter. Let's see, are there any? So what time is it? It's so maybe we can talk about some of these exercises. The ones that obviously we can't do the coding exercises, but we can do something about question answering. You know, answering these exercises. Anybody want to take a crack at answering number 1? What's the fundamental idea behind support vector machines?
So let me take a dig at that. So support vector, it is just a classification problem like other, but the thing that separates it from the other is that here the intention is to create a good margin between the classification, not just come up with a decision boundary that will somehow differentiate the two classes, rather create a margin of space. That is the like what makes it separate from the other classifiers.
Yep, that's 10 out of 10 for you. Yeah, I mean, you want to make the widest possible street, as he says. I like that language that he uses. The widest possible street between the two classes. So it's basically maximizing that margin. That's what support vector machines is all about. What's a support vector?
It is again on the same note. Actually, the data points which actually defines that street.
Yeah, and there was something interesting that when I listened to the lecture by Abu Mustafa, he mentioned this extremely interesting property of the support vectors, and that is that if you solve the problem and you find and you count the support vectors, the ratio of support. So a lot of times these a complicated problem, when you do the solutions and solve for all of the parameters, you'll find generally that there are only a few support vectors. And we'll go back to some of these. We go back to one of these plots, so we can see where it shows a problem like that. Where's a problem? Okay, so yeah, like here. So there's a support vector. There's a support vector. There's a support vector. So in this problem, it looks like there are. Oh, and then the ones that are. Let's see, what are these? I think he's counting. I think he's counting the ones that are outside the boundary, outside the margin as well.
Maybe this is a little naive, but the way I imagined it was that street is a synthetic vector plane.
Yeah, yeah. But the support vectors are the ones that are on that margin. I think that's the definition. And when you find the support vectors, it turns out that if you take the ratio of the number, you count up the support vectors, the ratio of support vectors to total examples gives you a lower bound on the generalization error. That's the really cool property of support vectors. So like if you have 1,000 data points and you have 10 support vectors, then the lower bound of your of your generalization error, that is 10 over 1,000 or 1%. That means that when you apply your model to new data, that it will be at least that good, that its accuracy will be at least that good. And that's a really interesting property of support vectors. This was in the lecture number 15 in the Caltech course by Professor Abu Mustafa. He didn't give a proof of it, but it's just a really interesting property because it gives you the ability to predict a generalization error, a lower bound on generalization error.
If I'm not mistaken, though, the support vectors are everything that lies within the street, including on the border, not just the ones on the border.
Support vectors are the ones that are on or inside the street?
Yep.
Okay. Is it spelled out in there anywhere in the chapter? Because I don't remember.
You can just click on the answers to the questions.
Oh, okay. So we go to that question, and then we click on that question, and then it will give us the answer.
Or here's a link at the end of whatever. Just go to Appendix A. The click.
Appendix A. Okay.
Yeah.
Okay. So now in here, oh, why doesn't it take me there? No dictionary results. So this is not working for me.
Probably try command instead.
Command what?
Just command on your keyboard, or sorry, control on your keyboard, and then try clicking on appendix.
Control click. Okay. That didn't work. How about Alt? Nope. It doesn't seem to like that. Shift. Ah, there we go. Shift. There it is. Okay. I did a shift click. That did it. Okay. So where are we?
Chapter 1, though.
Oh, yeah. We want to go to
Chapter 5.
Chapter 5. Chapter 5, support vector machines. Fundamental idea, separates, blah, 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 blah. Support vector is any instance located on the street, including its border. Okay, so that means, yeah, if we have a street, then anything in between those two margins, right? That's what you were saying, Srinivas, right?
Yes.
Okay. Any instance that is not a support vector off the street has no influence whatsoever. You could remove them, add more instances, or move them around. As long as they stay off the street, they won't affect the boundary. Computing predictions involves only the support vectors, not the whole training set. Okay. Okay. Well, yeah.
Like a bit surprising. Support vector is supposed to be on the decision boundary, right? The inside or outside points are just data points which we need to classify. How come the inside points are support vectors as well?
Now, all the points inside of the street are support vectors. That's the definition of the support vector for the general case of the SVM.
If you go to the code that is there associated with that notebook, there is a particular piece of code that he has written for printing those support vectors. That's why you can see the support vectors are that color, some pinkish color, something like that.
Okay, so is it like right here, or
yeah.
Okay, well this is for regression, right? Let's go back.
So he has written a certain code for this one. This one here. Okay.
Okay.
Find support vector. See the function. There is a function find support vectors.
Yeah, I remember seeing that function.
I saw that function here.
Yeah, I saw that function too. I'm trying to find where it is. Let's see. Find support vectors. If anybody knows where it is or which way I should scroll, let me know.
You can search for that probably. That will be easier.
Oh yeah. Let's see. Find in page. I have to do.
Find underscore support underscore vector.
Okay. It's called find support.
Support vector. Yeah.
Okay. There it is, right there. Okay.
Here you can see their
off margin. Return anywhere off margin. This is for regression. Okay, so it would be the opposite for classification.
The classification, right?
Yeah. There's no function find support vectors for.
You go up a bit.
Yeah.
Because depending on that thing, that if you see those data points, those are a bit pinkish data points. Those are support vectors.
Yeah, right here. So.
Yeah.
So let's see. Yeah. So. Does he have a find support vectors function here? Support vectors index. Okay, so So where does he plot with the pink? Let's see,
That's
plot.
a function actually. Plot support vectors or something like that. It was.
Plot SV decision boundary. So that's probably this one.
That's the decision boundary, right?
Yeah, but plot.
In the hard margin case, it should be the ones on the boundary, right? In the soft margin, it obviously should be affected with what is within the street also.
Yeah,
Yes,
that's right.
In the
That's
general
right.
case of the SVM, which is the soft margin, then it includes. But in the hard
Everything
margin,
within.
obviously, there's nothing
Right.
inside
Yeah.
to begin with. So the definition
Yeah.
simplifies to on the border.
That's right. That's right. That makes sense.
Right.
So I had a question with RBF. Like intuitively, if you think of RBF, since it's just a exponential or a Gaussian, all you're trying to do is just find like a weighted distance from your current point with respect to all the other data points, right?
Yeah, I mean that. Yeah, looking at that function. Yeah.
So it's like you're trying to create this new dimension with respect to each data point. I'm just trying to understand like what exactly this kind of space is like. Does that make sense, or is there something else that I'm missing there?
Well, okay, so it'll be depending on the on the value of gamma, which tells you how narrow or wide the Gaussian is. You can just visualize this three-dimensional Gaussian surface, and centered around some point, and then the Gaussian, that function just tells you that if the point is near it, then that function is large, and if the point is far away, then it's small. So
okay.
Yeah. So your intuition is right. See where I want to get back. I want to get back to where we were. I'm not very good at navigating in this Kindle.
You can go to 172,
space.
page 172.
Yeah. How do you tell it what page to go to?
No, you go to the bottom of the page. Go to the bottom of the page with the mouse.
Oh, go to the bottom.
Then.
Yeah. The problem is I've got this. There it is. There we go. Okay. So now I can.
Slider. Yeah. From using the slider, you can.
Yeah. Okay. So I want to go back to one something in the 170. Yeah. Good. Thank you. Okay, that's close enough. It's 172 back here. Okay, there's exercise. Okay, so now we talked about support vectors. Why is it important to scale the inputs when using SVMs?
Isn't it the same as like keeping numbers in fractions versus in millions or thousands?
Yeah, I think he has a draw. He has a plot of that somewhere here. Let's see, where there's unscaled data and data scaled differently somewhere in here.
I think it's near the beginning of the chapter.
Near the beginning, yeah. Here, unscaled data, unscaled data. So, I mean, on the face of it, you see that that looks like a very narrow street, and this is a much wider street. But I'm not so sure because the scales are different. He does have.
So basically, by scaling the data, you come up with a higher margin. Higher of the street.
Yeah, because this point turns out to be on the margin for the scaled data, but not on the margin for the unscaled data.
Isn't it just that one dimension would overwhelm the other dimension if one is bigger than the other? So your street is going to be
smaller values will get lost.
Right.
Yeah, that's sort of the general idea why you want to scale. You want to make each dimension count the same in some way. Okay, back to 170.
Yeah, about that image, shouldn't the scale data change the points position?
Sorry?
You're going to the previous image on the scale.
Yeah.
I wonder why the dots are not changing much in the scale data.
The dots are not changing much in the scaled data.
Yeah.
Well,
yeah, if you look at the axis numbering, it's quite changed.
Everything is relatively, will be the same, right?
Yeah.
So the 2 points on 5, 5 will still be at 1. what is that? 50,5 and 0,5. I mean, 25,5 has to still be on one.
What about the vertical axis?
The horizontal axis also gets rescaled because remember you subtract the mean and divide by the standard deviation. So
right. So relatively everything has to still be on the, like whatever is on a line, if you're doing a scaling, will still be on the line, right?
Well, apparently not because, well, yeah, I mean, the things that are on the line are still on the line after the scaling, but this thing was off the line before the scaling and
no, not the line like
line.
that. I mean, that the point that you're pointing at right now is like on the y-axis. If you're looking at, I'm sorry, yeah, exactly. So those 2 points have to still be on the same thing once you scale them, right? So that's why those 2 points are still on the right figure.
Oh yeah. I see. These 2 points here are lined up. Yeah, that's right. Okay, shall we go back to the questions? Let's see. Back to 172. That's too far. That's close. Oops, one more page. Okay, should use the primal or, wait, can an SVM classifier output a confidence score when it classifies an instance? What about a probability? Anybody have any idea about that? Well, wouldn't the distance from the margin be some kind of a confidence score? In other words, if you could say that, oh, this point is way outside the margin, so I'm pretty confident in its class. Otherwise, and this other point here is actually on the street, so I'm not so confident in its classification. It would seem that the distance from the margin is some kind of a confidence score, or it could be used as some kind of a confidence score. What do you think about that?
Distance from the margin sort of ratioed with how wide the street is, right? Something like that. I would also imagine could help.
Yeah.
Giving you some
scale it, divide it, normalize it by the width of the street. Like that's what you're saying.
Yeah.
Yeah. I think that would be
good. that would normalize the distances. I see.
In other words, how many street widths are you away from the? How many street widths are you away from the margin? And if you were very close, if you were like 1 street width away from the margin, well, that's good, but it's not as good as being 10 street widths away from the margin, right?
Okay. And okay. Yeah.
And what about probability? Well, that is considered one of the failings of the SVM. One of the shortcomings of support vector machines is you don't get a classification probability. Although haven't read, but I think people have actually tried to derive probability scores for the points, and there are mathematical schemes to do that outside of SVM.
It's like applying a classifier to the points outside after you have applied an SVM, which is what you are talking about, that Raquel mentioned, or you're talking about. That's you classify the points outside and get probabilities based on the distance from the edges of the SVM classifier. And that way you get a probability, but you don't get a probability from the base SVM.
Yeah, but and so like putting these margin distances through a sigmoid function could map them to probabilities, right?
Yeah, logistic regression of the points outside can get you that.
Yeah. So using those, using the distances or the scaled distance as Raquel suggested, and mapping those and putting those scaled distances through a sigmoid might be able to give us probabilities.
Man, we are fancy now.
Yeah. Yeah. So 5th question is, should you use the primal or the dual form of the SVM problem to train a model on a training set with millions of instances and hundreds of features?
Use the dual when you have more features than instances, right?
Yes, but in this case, you have only hundreds of features, whereas millions of data points. So this wouldn't be that case, right? this wouldn't be the case where you'd want to use the dual, right? Because in the book they said that if you have more features than data points, that's the reason why you want to use the dual, because it's faster in that case than the primal.
Right, for fatter matrices, basically, right? Not
fat, yeah, fat instead of skinny, yeah,
right.
design matrices. Okay, what about this one? Say you've trained an SVM classifier with an RBF kernel, but it seems to underfit the training set. Should you increase or decrease gamma? Remember that gamma controls the width of the Gaussian in an inverse way. So the smaller gamma is, the let me see, gamma is inversely proportional to sigma squared, and so large sigma, that is wide Gaussian, means a small gamma. So just bearing that in mind, decreasing the gamma makes it what did I just say? Decreasing the gamma makes it wider, makes the Gaussian wider, and increasing the gamma makes the Gaussian narrower. Okay, with that in mind, and we are underfitting. So do we want a wider or a narrower Gaussian if we're underfitting?
For underfitting, we probably want to make it narrower, no?
Yeah, and to make it narrower, we would have to, I keep having to think about this. To make it narrower, we would have to
decrease gamma.
Decrease gamma. No, increase gamma.
Increase gamma.
Right. Increase gamma makes it narrower, yeah.
But what was the intuition? I kind of missed something there.
Oh, the intuition is that if you have a broad gamma, that's sort of a sloppy fit. You're not fitting things. A broad gamma is kind of leaving a lot of margin for.
So broad gamma is basically a much tighter Gaussian, right?
No, that's a broad gamma is a wider Gaussian, right? Broad gamma. Sorry, I'm talking about Gaussian. The Gaussian. You want, if you're underfitting, the Gaussian is probably too broad, so you want to sharpen it up. That's what I'm saying.
Oh, okay. Yeah. I see. Okay.
Yeah.
Figure 5.9 kind of helps in the chapter.
Which one?
Figure 5.9.
Oh, figure 5.9. Okay, let's see. Let's find that. Figure 5. I can't see the figure numbers. What page is that on? Do you know? Maybe it's easier to find it by the page number.
Go back. It's 5.11 that you're on.
Okay, back.
170.
170. Okay, 170. Oops, I almost had it. Okay, 165. There it is. Pull it back up. 5.9. Figure 5. I don't see it. Figure 5.9.
Should be right before the computational complexity.
The one to right.
Is it back this way, or come to think of it, I don't. There are some figures. This is 5.13, so it must be. What's this?
There, that's it.
This one here.
That's it. Yeah.
Okay, so there's the small gamma, and so this is wide. A wide Gaussian. It's not even doing a good job of making a curved surface at all. And then increasing gamma means the Gaussian is sharper, and so now it's localizing more around here. And then there's two things going on here, right? There's the C parameter as well. And the C, remember, the C controls the allowance of margin violations. So there's two, and both of these things, both of these parameters, in a way, can be considered as regularizers. And so, regularizers are what you want to do when you want to change the regularization to go from overfitting to underfitting, or from underfitting to overfitting. Okay, back to.
So once again,
Joseph, your intuition of the thing is right on. As a memory aid, I just remember that gamma and C move in the same direction and C moves inversely. So gamma moves inversely as well.
Yeah, I just always have to stop and figure it out every damn time. So
to avoid that, I just think gamma C move in the same direction, and it's opposite to what you would do in lasso and stuff. So if C gets lower, you increase regularization. When C goes higher, you reduce regularization, and then you can relate it to the bias.
Gamma goes the same way, yeah.
So in that figure, you had like 4 images, right? So which one is the most regularized that you would pick?
Okay, let's go back to that one.
Higher C, most regularized is low C, low gamma.
So that's the top right, right?
Don't recall.
Low C, low gamma is top left. Right? So that's
given this problem set, like if you were to choose, which one would you choose? Like the most regularized? That's why I was kind of wondering. I first thought the other one you're currently pointing at, but then I was like, nothing is covered outside those boundaries.
Right. I pick this one actually, right? Because what about what about if points came in over here? You wouldn't know what to do with them. You classify them as green. That would be pretty bad.
Right. Okay. Yeah.
Okay. Do you want to go on? It's 8:37. We're a little over, but if you want to continue, we can. Let's see, back to page 170. Oops. 170. No, this Kindle thing is just not as good. I think they may, if you don't have the Amazon Kindle, this thing just sucks. This interface just really sucks.
Do you have the PDF book?
I have I'm viewing this thing in the Kindle Cloud Reader, right? I got the Kindle version, right? So I'm viewing it in the Kindle Cloud Reader, but they deliberately make it very rudimentary and a crappy interface so that you'll go and buy the Kindle because that has a really nice interface. Anyway, so that's my rant. But okay, save train, blah, blah, blah. How should you set the QP, quadratic programming parameters, HFA and B to solve the soft margin classifier using an off-the-shelf QP solver? That's something we probably take a little more time on. We probably don't want to do it right on the spot here. But if you go back to that, the equations that he gave, the equations that he gave right before the dual, right in that quadratic programming section, he gave sort of the general expression for a quadratic programming problem. And so you just want to think about how that maps to, how equation 5.5 maps to the soft margin problem, which is 5.4. That's what he's asking there, and it takes a little thought, so I don't think we should try to do it right now. Here's one that you have to write some code, and here's one you have to write a code, and so the rest of them you have to write code for. So I think this is a good place to stop then.